Let's see. All of the notes up to today's lecture are now posted, and all of the video recordings up to Monday's lecture are there now, so come and get them. I also reposted the notes regarding the hyperfine interaction. These were notes number 4. I had noticed some time ago that there were some fatal flaws in the way that was discussed originally, and finally got around to correcting that. So get a fresh copy of those for the future. All right. So last time we were continuing our discussion about the atomic structure of atoms in general, atoms with more than 1 or 2 electrons. And so what we discussed is that one approximation that we can make, and that captures the core properties of atoms, particularly the chemical properties, reactive properties of atoms, is to make the so-called central field approximation. That is to say that each electron sees the central field of the nucleus, and the effect of all the other electrons, its Coulomb force on one particular electron, is also a central force. That central force is some effective shielding potential that shields the nuclear positive charge, shields it with some amount of negative charge. So that we have some effective potential seen by each electron. We'll discuss that a little bit more in detail today. And that effective potential is a central potential, as I say, it's spherically symmetric. Okay? So under that approximation, we have, we can say that each of the electrons sees a central potential, and therefore the eigenstates associated with the energy levels of that electron are eigenstates with the same quantum numbers, the same kinds of quantum numbers that we assign when we talk about hydrogen. That is, because it's spherically symmetric, then we can separate out the radial motion from the angular motion, and the angular eigenvalues are the usual LMs for the spherical harmonics, and then we have what we call the principal quantum number, which is really the radial number of radial nodes plus L plus 1. And when you solve the radial equation with this effective potential and an angular momentum barrier, you get a radial wave function which has some number of radial nodes. And we call the principal quantum number n sub r plus L plus 1, because in hydrogen, the energy only depends on that. Okay? That's not true in general. So this is really the basis of chemistry, this central potential approximation. And so one obtains a sort of coarse description of the energy levels of multi-electron atoms by filling up these orbitals, from the lowest energy orbitals, fill them up with all the possible values of m sub L, and of course m sub S. You can have spin up and spin down. So of course we have 2 possible electrons in this orbital, 2 possible in this, 6, 2, 6, 2, 10, etc. Right? And as we discussed, the energies of states with different L are quite different because of the angular momentum barrier. That is, and we'll discuss that a little bit more today, that is, the electrons that have higher angular momentum are restricted to get too close to the nucleus because of the angular momentum barrier, and because of that they see more shielding, and therefore they're less tightly bound than the electrons that have lower angular momentum. And there's a competition between the number of radial nodes, which gives me a higher energy, and the angular momentum barrier, so that you have the transition metals in your periodic table where you fill in the 3Ds after you filled in the 4S's, even though from the point of view of hydrogen, this is a higher energy orbital than that. It's not true for atoms with more electrons. Right. So if we want to have a more quantitative description now of the state of a multi-electron atom, we do that. We need to respect the Fermi statistics, as to say the state of the system must be completely antisymmetric under exchange of all of the electrons. And we can write down such a state in a couple of ways. Actually, very convenient way to do this, and it's done in thinking about many-body physics, particularly condensed matter physics, is to use the machinery of so-called second quantization. So one would say the state of the system involves some number of particles, say electrons, and then a state where one of the electrons is in a state of certain quantum numbers that are noted alpha, beta, gamma, delta, etc., I would create an electron. So this would be the equivalent of what we would call a product state. It's not really a product state because we have to anti-symmetrize this with respect to all of the electrons. And this gets, I just want to make a little aside here. Some of you know about the whole business about entanglement, right? Entangled states are states that can't be written as, for a pure state of this sort, that can't be written as a product state. That is to say, it's some superposition of product states. Now, when we have identical particles, and when those two identical particles can have strong spatial overlap, we don't have strong spatial overlap, we can forget about identical particles. This is constantly forgotten. But if the two particles never get near one another spatially, for all intents and purposes, they're identical. I mean, they're distinguishable. There's the particle that's in that ion trap, and there's the particle in that ion trap, and I don't care, it's that ion. It's not in some way anti-symmetrized with all other ions in the universe. But if the two ions start to have spatial overlap, or the atoms start to spatial overlap, then I care. So there's a lot of confusion in the literature about is there entanglement in a single Slater determinant, or in a single state like this. I mean, this state, for all intents and purposes, is what we would call a product state, even though it's not really a product state, because we have, if I write out this determinant, right, I'll have the superposition of all different states with different products of these orbitals. But that's really not, in some sense, useful entanglement. So the entangled states that we care about in the context of identical particles are superpositions of different Slater determinants. If you have the single Slater determinant, for all intents and purposes, that's not an entangled state. Just a little aside there. So we should think about this as an ansatz that's like a product state, but that respects the identical particle statistics. Okay. So we want to now determine what this effective potential is, and to what degree we can think about it as a central potential. And one way to do that is to, as a first approximation, to make the so-called mean field approximation. The mean field approximation is saying that the electron repulsion that an atom sees, or an electron sees, is the average effect of all the other electrons. And we can formalize that by saying, well, let's look for a self-consistent solution to the Schrödinger equation, where we will take as our ansatz a Slater determinant, meaning we will populate the electrons in particular orbitals. And what I mean by that now is a joint orbital that involves both the spatial wave function as well as the spin state. So this could be, if this were 2 by 2, it could be, the same 1s orbital, 2s orbital, say, but with a spin up and a spin down. Okay? And then we look at the expectation value of the Hamiltonian in such a state, and we minimize with respect to the functions, that's to say the orbitals, the spatial orbitals, that give us the minimum energy. That's how we can find the ground state. In more general, we would find the stationary points, and that is enough to find the excited states as well, but let's focus for the moment on the ground states. And when we do that, we get what's called the Hartree-Fock equations, coupled set of PDEs for the, there's an important. Sorry, let me just put this in here. So these are a coupled set, they look like Schrödinger-like equations, but they're coupled Schrödinger equations, coupled between the different orbitals. They're not independent of one another because they have to self-consistently minimize the energy. So what do we see in this equation? Well, we see the bare attraction to the nucleus, and then we see the repulsive energy between electrons. We see a term here which is what you might have if you only use classical physics and thought about these as little charge densities with some cloud or distribution of charge. You would average the charge density of one orbital over the interaction with the other. This is what's called the direct interaction. But we have to respect the Fermi statistics, and the two electrons are in the same spin state. If the orbitals here labeled by the Greek letters have the same m to the s value, that is, say they're both spin up or they're both spin down, then we have to subtract out some of the effective interaction due to the fact that we can't have two electrons at the same place at the same time in the same spin state. That's the Pauli exclusion principle. And so we have the exchange term. Okay? And this is related then to this eigenvalue times this original state. So this is a coupled set of Schrodinger equations coupled between all the orbitals in the particular configuration of interest. And then one has to just solve this. Impossible to do analytically, but one can at least attempt to do so numerically. And, there are probably, these ancient codes written in Fortran 66, which, reside somewhere in Argonne National Laboratories that have been constructed and, probably don't run on modern processors anymore, but they're out there. So, how do we interpret this equation? Well, firstly, what is this energy here? We should think about this as the energy associated with the electron in this particular orbital. So we can think about it loosely as the binding energy, if we're interested in the bound states here, of that electron in the atom. Let's say how much it would take to, if we applied that amount of energy and we were able to then ionize and remove that electron, that's how much energy it would take. Now that's not exactly true because it doesn't take into account how the self-consistent energy changes once that electron's missing. But it's coarsely that. So now the question is, in what sense is this the central field approximation, the central potential approximation? Well, it's not actually exactly that, but it is that for the case of a closed shell, and that's what I want to discuss a little bit right now. So if I have a closed, when I say shell, I really mean subshell. States with this, all of the orbitals with a given NL, which there are two L plus 1 times 2 of those. So let's look at the R25. Closed subshell. So, what I mean by a closed subshell there are 2 times 2 L plus 1 orbitals with given NL. So let's say all m sub L values and all m sub S values are consistent with a given NL of that orbital. Okay, I could also have multiple n. So I mean, example could be, I'm looking at, one of the noble gases, right? You could be looking at argon, which has many closed subshells. Or the group 2 elements, for example. Group 2 elements have both the closed n equals 1 and then a closed subshell, or whatever n it is, whatever mobile gas, and then I have the next n with the 2s orbital filled in the group 2 of the periodic table, right? So that's another example of the kind of configuration I might be considering. So what's the first thing we can say here? Well, let's rewrite this equation here. What I have then is let's write it in position space. That's my kinetic energy operator. I have the attraction to the nucleus. I have a particular orbital with these quantum numbers, with some particular m sub s. But there are two in this sum. If we come back to this equation, there are two orbitals with the same spatial orbital, but two different spin states, because this is a closed subshell. So for a given term, there'll be two different u's that appear in the direct interaction. Both terms appear. So I end up with 2 sum over n prime L prime m sub L prime integral u and then I have only one exchange term, because only when the two electrons have the same spin state. So there's only one, for every pair, there's only one term. I'll have the same sum. Okay? So that's our Hartree-Fock equation. Now what makes this particular, in that it's a closed subshell, is that the sum here over m sub L goes over all possible values. Goes from minus L to plus L. That's what makes this a closed shell. Also, of course, we had all of the m sub s's. So, what can we say about this? Let's do a little aside over here. Let's look at the direct term. That's this term over here. Let me, before I do that, let me write my spatial wave function. It's got a radial. Now, this notation is just the standard in all these quantum chemistry things. You know, before we called U the reduced radial wave function. Now we're not calling it that, so I'm sorry. But that now U is the whole orbital, and we'll call the radial part P. So this is what we called U before.
In the homework, U is U1, right? I mean, it's the reduced.
I don't remember. I'll look at it afterwards. I'm thinking it, but I don't remember. I'll look at it. One second. So this depends on it. Okay, so now let's look at the direct term. I'm going to bring the sum over NL prime inside the integral. So I end up with So the key point here is that because we have a closed shell, this sum is actually independent of theta and phi. No matter what theta and phi is, if I sum over all L length of L, I can use the completeness of the, this is essentially a projector onto the space, and that projector is equal to 4 pi over 2 L prime plus 1, independent of theta and phi. Okay, that's just the property of the sum, is sometimes called the addition theorem. It's basically the fact that it's a projector. One way of saying it. Okay, so so now let's see. I'm missing some factor. It's driving me nuts, but I don't remember what it is. Let me just take a peek back at my notes. Try to remember what I was doing here. Oh, okay. So far, so good. Except that I got it backwards. That's why it's confusing me. Okay, seems better. Okay. Let's see. All right, so now we want to do this integral. This is an integral over, I'm being a little bit sloppy here. It's an integral over the prime variables. We have to separate this in terms of the addition theorem. This one is the other way, that's why I think I'm confused. And then the sum over L, the sum over N, and then R greater than to the L, R less than to the L plus 1, Y star Lm of theta and phi, Y Lm of theta prime and phi prime. Okay? So now we can do that integral. If we integrate this over all solid angles associated with the prime variables, the only thing that depends now, because this sum got rid of any of the theta and phi dependence associated with this orbital once we summed over the closed shell, the only remaining term that depends on those variables is here. So note the integral over all solid angles of YLM of theta and phi prime, well, that's going to be 0 unless L and M are both 0, right? Because of the orthogonality of the spherical harmonics. So if I wrote this as this is delta L0, delta M0, using Y0, 0, U1 over 4 pi. So then I do the sum over L and M existing over here. But the only term that's non-zero is the one where L equals 0 and the one where M equals 0. So I replace this with L equals 0, so 1 over R less than. Which one is less than, which one is greater than? Is greater than in the denominator? I think greater than is in the denominator. Yeah, sorry. Remember the notation here is this is either R prime or R depending upon which one is bigger. And the bigger one goes at the bottom. So I replace L by 0, I replace M by 0, so I get another Y0, 0, which is equal to 1 over root 4 pi. But that cancels this guy over here. And putting that all together, I get the V direct term is equal to the direct potential is twice the sum over n prime L prime, the integral from 0 to infinity dr prime. I have a 2 over 5 plus 1. Sorry. So, what I see here is the direct potential, this term in the Hartree-Fock equation looks like this. It is spherically symmetric. It does not depend on the direction of R. It only depends on the magnitude of R, because what is R greater than? Well, I mean, so this is equal to, if we can break this up into two integrals, an integral in which R prime, or R is bigger than R prime, so up from R prime goes from 0 up to R. This is a correction that looks like a Coulomb potential with a 1 over R term. And then we have a term from R to infinity. That's what that means, right? R greater than means if either R or R prime, depending on which one is greater than, which one is bigger. So as you see, this potential is only a function of the magnitude of R. It does not depend on theta or phi. So it is indeed a central potential. Now we could do the same thing for this. It's a lot more complicated. And I tried to see if I could find a simple way to get at it, but it's a mess. You really need the Wigner-Eckhart theorem or some better notion of the addition of angular momentum than we currently have to be able to get this. But the truth is that this is also, the indirect term is also central, the exchange term. So, if I have a closed shell, this is equivalent to a central field approximation. In a closed shell, or a closed subshell, I should say, where we have all possible m sub L values and all of the electrons are paired, as we think about this in, in our chemistry picture of pairing electrons in a spin up and down. The charge density associated with that atom is a spherically symmetric one if it minimizes in the mean field approximation. The mean field approximation that minimizes the energy is a spherically symmetric configuration. Now for open shells, that's not exactly true. There is residual terms that depend on the actual directions of the electrons. It's a smaller effect, but it's there. And that leads to what we call electron correlations. As I said, in the Slater determinant, the electrons are kind of correlated, but they're not really, right? There's this orbital for that electron, there's this orbital for that electron, etc. We put each electron in a specific orbital. We don't know which electron is which, so we have to anti-symmetrize. But there is an electron in this orbital, there is an electron in that orbital, etc. Correlation effects means they're superpositions where where the electrons' configurations are different. Okay? So what we want to talk a little bit about now is the effect of electron correlations. Let's write down, let's say, we have the exact Hamiltonian, which I can write in the following way. I have the sum over, when I mean exact, I mean up to whatever level of approximation we're doing, and let me explain what I mean. We have the hydrogenic type Hamiltonian. We have the screening potential. Then, of course, we have the actual repulsive energy between different electrons. But we're going to look at the difference between that and the mean field or central potential. So this is the central potential or the mean field potential in the case of well, I'll come to that in a moment. In the case of a closed shell, this term is 0. And then, of course, we also have other correction terms. For example, we have spin orbit coupling. Of course, then we can add in hyperfine if we like. Now, either of these terms, the terms that have to do with the non-spherically symmetric nature, or non-central for each electron, or this term, in which we know we have to, we know when we couple spin to orbit that the eigenstates of this part of the Hamiltonian are the eigenstates with a given J for each electron. But a given J for a given electron is not a single electron orbital with a spin. It's a superposition of those. So no single Slater determinant is going to be able to diagonalize this effect. So in this, let's look at the good quantum numbers of each of these effects. Here, the good quantum numbers well, we had L for each electron, M sub L for each electron, and M sub S for each electron. We specified the configuration that way. These are not the good quantum numbers here. Here the good quantum numbers are J sub I, L sub I, and M sub J sub I. Of course, S is fixed. I fixed S as a half, or S sub I is a half. What about in this case? Well, in this case, the individual L's are not good quantum numbers. Because this, if I just remember, L is the generator of rotations. If I just rotate the position of one electron without rotating the other, well, then the distance between those two electrons is different and the repulsion is different. This Hamiltonian, the good quantum numbers are the total L and the total M sub L. Now, of course, in addition, this doesn't depend on spin. But if I rotate all the L's together, I should rotate all the S's together. So these are the good quantum numbers. So whether we can write this as a Slater determinant, where these are the good quantum numbers, or we need to think about these quantum numbers or these quantum numbers, depends on which are the dominant effects. As we've discussed, there are only sort of effectively good quantum numbers. None of these quantum numbers are exact. The only exact quantum numbers in this problem are the total J and total M sub J. Because the total angular momentum is conserved. Now that's not true either, because of course then we have nuclear spin. And if we were to add the hyperfine interaction, well then the only real good quantum number is the total F and the total M sub F. So, how one defines the energy levels of the many electron atom depends on which of these terms dominate. We start with this as our base description. In our base description, we have electron configurations with these quantum numbers. Then we add in the perturbations. And the question is, which is a bigger effect? Do we first couple the electron spin to its orbit, get individual J's, and then couple those individual J's together to get the big J? Or do we first couple the individual L's together to give a total L, and the individual S's together to give a total S, and then couple the total L to the total S to get a total J? They will be different descriptions and have different effective good quantum numbers. And if these terms are of the same order, well then neither of these quantum numbers are good. So that gives rise to what are called different coupling schemes when one talks about the more exact description beyond the Slater determinant and the mean field approximation. One talks about different coupling schemes. If spin orbit is small compared to corrections to central electrostatic force, what we say is we have LS coupling. And this is also known in the jargon of atomic physics as Russel Saunders coupling. In that case, the good quantum numbers are L, S, J, well, L and S, and then if we ultimately add in spin orbit, which we can do after the fact of the perturbation on this J. Alternatively, if spin orbit dominates, then we have what is called JJ coupling. Where first we couple the individual orbital angle meant the individual spins get individual J's. And so the good quantum numbers here are the set of all the J sub i's and M sub J sub i's. Of course, here M sub F and M sub S is also a good quantum number. But we typically don't specify that because the energy is degenerate in these different quantum numbers. Now, when could we imagine this effect dominating? Remember that this coupling here depends on the speed of the electrons, right? Because the faster the electrons are moving, the bigger the magnetic field they see in their reference frame, and therefore the bigger that effective magnetic field couples to their intrinsic magnetic moment. So this effect dominates for very heavy atoms, whereas the Russel Saunders is appropriate for lighter atoms, right? Because the higher Z as we looked at in our first problem set, when we looked at how the scaling, we saw that the speed of the electron, it can be highly relativistic when we start having the atoms bound very tightly to the nucleus. Okay. This is not familiar stuff to me about how you describe these really heavy atoms, like a lead or something like that. But there is a transition, as I said. Neither of these are exact. It's kind of like you remember the problem that we had for homework where we looked at the Zeeman effect in hydrogen. When the magnetic field was small compared to the hyperfine interaction, M sub F was a good quantum number. When the magnetic field was large compared to the hyperfine interaction, and we're in the so-called Paschen-Mach regime, the M sub J and M sub S were the good quantum numbers. But for a magnetic field where those two interactions are on the same order, neither is a good quantum number. You have some kind of transition between them. So there is an intermediate regime where neither Russel Saunders nor J-J coupling is good, and you don't have any of those quantum numbers, you only got J. All right, so with that said, how can we then do perturbation theory in order to, well, it's complicated because we need to know exactly its potential, but what can we say about the nature of the perturbation theory? Let's look in a regime, let's consider a case where So the LS coupling, the interaction, I'll call it delta V, we want to diagonalize this. However, what are we diagonalizing it, and what basis are we diagonalizing this? We're diagonalizing this in the basis of Slater determinants. That's to say, we've solved the Hartree-Fock equation for a particular set of orbitals, for a particular configuration, the self-consistent solution that minimizes this energy, or is a stationary point, is an eigenstate of that energy. We then have these configurations, and now we want to use them and perturb the energy levels by adding in additional effects. Now, when we specified the Slater determinants were specified an electron configuration. And we specify that configuration by what the NL orbital and then the M sub s, that's to say up or down. Hidden within here is the M sub L value. In other words, if I don't have a closed shell, there are multiple Slater determinants that all have the same energy. Okay? So in the central potential, energy depends on NL, not M sub L. So, we do degenerate perturbation theory. We have a set of degenerate Slater determinants associated with different possible choices of M sub L. And then we diagonalize this correction to the central potential in the basis of those Slater determinants. And we know that when we do that, we end up with new quantum numbers, L and M sub L, and S and M sub S. So what one does, without actually getting into what the actual diagonalization is, we want to know what are the possible values of the total angular momentum L and the total spin angular momentum, capital S. What are the possible total quantum numbers, which are known as the terms? So diagonalization of non-central potential leads to what we call terms. That's the language that's used. And the term is, so the set of possible orbitals NL are called an electron configuration. The coupling of that configuration to give a particular total L and total S is called a term. And we specify those states in the following spectroscopic notation. The multiplicity in the total spin is up here as a superscript on the left, and then the total angular momentum is given as L. Now we've seen this already, because we did this kind of diagonalization for the case of helium. For the case of helium, when we looked at the excited states of helium, we didn't talk, in the case of the ground state, we had singlet S0. And in the case of the, when we had one of the orbitals as a excited orbital and one of the orbitals as a ground orbital, and then we diagonalized this, we ended up with singlet and triplet pairings, right? And that was not a single electron configuration, it was different electron configuration corresponding to different M sub L's and different M sub S's correlated in a particular way. So, first statement, for a closed subshell, well, if I have a closed subshell, I have all possible M sub L's and all possible M sub S's because I filled up the whole subshell. So M sub L, which is the sum over all of the electrons M sub I, in this case, is 0 for a given L, going from minus L to plus L. And similarly, this is also 0 in a closed shell. So the M sub L value has to be 0. The M sub S value has to be 0. So there's only one possible value of total L that can always give M sub L 0 and M sub 0. It has to also be the case that the total L is 0 and the total S is 0. Otherwise, if we had other values of the total L and the total S, we would get different projections. So for a closed shell, we have to have a closed shell as a singlet S. We think about a closed shell as all electrons paired together. For open shells, life is more complicated. For open shells, we have to think about what are the possible values of so we need to enumerate possible values of capital M sub L and capital M sub S consistent with Fermi statistics. And that's a little bit of a pain in the butt. For the case of, if I have example, if I have electrons in different NL orbitals, for example, so this would be an excited state of carbon. Carbon has its last subshell. I excited one of those electrons. And I want to know what are the terms of this. Well, because these are non-identical orbitals, I can have the symmetric combination of this or the antisymmetric combination of this. And that's paired appropriately with singlet or triplet, just like we had in helium. So if I look at this and I ask what are the possible values, well, what we see here is that because L1 equals L2 is 1, and the two electrons have spin 1/2, that the total values of L can be either 0, 1, or 2 when I add these together. And similarly, S can be 0 or 1 for singlet and triplet for this pair of electrons. So the possible terms are the singlet S or the triplet S, the singlet P or the triplet P, and a singlet D or a triplet D. Those are all possible terms. Now the question is, which is the lowest energy state of these possible terms, which are correlations of this configuration? Well, that's not the easiest thing, but there are sort of empirical rules associated with that. And they're called Hund's cases, or Hund's rules. Not really rules, they're kind of rules of thumb. The state, or the term, with largest S has lowest energy. And the second rule within, for given S, remember S means two different things here. So much annoyance. For given S, state with largest L has lowest energy. Why is this? Well, this rule we've already discussed. Because if the electrons are paired in a triplet state, for example, if I had 2 electrons, that's a state that has a bigger S than if it's in a singlet. If it's symmetric in spin, then it's antisymmetric in space. And if it's antisymmetric in space, that means the 2 electrons have no probability of being near one another, and therefore there's less repulsive energy. Therefore, they're more tightly bound. And that's true for many, had more than 2 electrons. The higher the symmetry in S, the bigger the antisymmetry in space, and therefore the bigger the electrons, the more time they spend away from one another, and therefore the more tightly they are bound and the lower energy. So that makes sense. But what the hell does this mean? I thought that we said that the states with low angular momentum had they were the states that had less angular momentum barrier, and therefore they were closer to the nucleus, and therefore they were more tightly bound. So what the heck does this mean? This is saying the states with the largest capital L tend to have the lower energies. Well, what this is not about the individual L's, but about the total L. And a way to think about this, although I don't know how, I mean, I just, did the usual look at Wikipedia kind of thing. Well, Wikipedia was a better site, but it was the same kind of idea. The physics forum, which is of sorts. States with large L can have large M sub L. And what that means is that the orbital motion adds up projected along some axis. So if I think about this classically, there are orbits in which the electrons are going in the same direction, and those add up to give me some big L. Whereas if I have a small L, then that tends to come along with electrons that are going in opposite directions. This is their orbital motion. And electrons that go in the same direction can, in principle, always stay far away from one another. They start on opposite sides of the nucleus, they can stay on opposite sides of the nucleus. Whereas electrons that go in opposite directions are going to pass one another at some point. And so they'll tend to be near one another more of the time than electrons like this. Therefore, electrons like this will tend to have a lower energy because there'll be less repulsion. Therefore, the states with the larger L tend to have a lower energy. Do you buy that? Maybe. Seems a little weird to me. I mean, the electrons are wave functions. They're not doing this. What the heck are we talking about? I don't know. If anyone can help me understand a better explanation of this Lenz's rule, please tell me. But with that said, we can then look at this particular configuration and the terms. So we have the configuration associated with this, which split up into singlets and triplets. The singlets were high energy, the triplets were low energy. And then we had the splitting associated with the different L's. And in this case, we had the singlet D, the singlet P, and the singlet S. And here we have the triplet D, the triplet, let me take this up a little bit just because I'm going to. Triplet D, the triplet P, and the triplet S. Okay. So one specifies the state typically by both a configuration and a term. That specifies the state, at least within LS coupling. Now, in addition, there is fine structure. Generally speaking, if we have non-zero angular momentum, we have spin-orbit coupling. So then we take the term and we perturb the terms with spin orbit coupling. And that leads to what we call the fine structure. So, the fine structure is in addition to L and S, where before we also had M sub S and M sub L as good quantum numbers, now we have J, L, and S, and M sub J as a good quantum number. So in this context, what is the spin orbit coupling? Well, the case of the singlets, the spin is 0. So there's no spin orbit coupling there. But in the case of the triplets, well, the spin is 1. And therefore, I can have spin orbit coupling, and therefore I have fine structure. So what is the fine structure? What are the possible values of J associated with this? When we do that, by the way, the term notation is you write the multiplicity, you write the total L, and the total J. That's how you specify these 3 quantum numbers. And then there's a degeneracy in M sub J. This is 2J plus 1 times degenerate. So what are the possible values of J in this case? So in this case, L is 0 and S is 1. Well, there is only one possibility in this case. You can only have, there is only J equals 1 because L is 0. I mean, these are all right? That's the value of J because in this case, J equals L here. What about here? What are the possible values of J? S is 1. L is 1. What are the possible values of J? 2, 1, and 0, right? So this splits up into a triplet P2, a triplet P1, and a triplet P0. And what about in this case? S is 1, L is 2, so I split up into a triplet D3, a triplet D2, and a triplet D1. So, multi-electron atoms are complicated. Let me just conclude this by just showing you the periodic table. So let's hope this works. Can you shuffle in for me, please? Thank you. All right, very good. Come on, I really need it. Come on, spinny ball. All right, excellent. Sorry. So, you'll notice, so this is the periodic table that you can download from this website. I recommend having a copy. And you'll notice maybe, I don't know if you can see because the resolution is pretty crappy on the screen, but listed here is the electron configuration and the term. So for example, the alkalis have 1 electron in the outer shell, and therefore all of the that orbital is an S. It's one electron, so it's only, there's no coupling of terms. The term is the electron orbital. We'll talk more about the alkalis on Monday, but they're all doublet S a half, right? The closed shell group 2 elements, as we said, all closed shells are singlet S0. As are, for example, the noble gases. And then you have all kinds of crazy stuff here. It's confusing to me that things like lead are still written this way, because I would think that LS coupling is bad. I don't really understand that, but something I'll have to explore and learn a little bit more. But you'll see that the energy, the electron information is there in terms of both the configuration and term. So now you can look at this periodic and say, yeah, I know what that means. All right, we'll conclude there. And starting on Monday, what we're going to do, we'll talk a little bit about the alkalis in particular, because they're a special atom in the context of modern atomic physics experiments and studies. And then we're going to start talking about the interaction of atoms with electromagnetic fields. All right, so that basically concludes our structure talk for the semester.